Hello, hello, hello. This is Nicholas, and I wanted to just make a quick video on general arc length. So in Calc 1 or Calc 2, you're probably familiar with this formula that the integral from a to b of the square root of 1 plus f prime of x squared dx, that's the length of arc of a curve f of x from a to b. And now I want to tell you that that formula is just a special case of a more general formula. And so what I want to consider today is stuff from Calc 3, arc length from Calc 3 for any generic vector function of n dimensions. And then I will show that this is actually just a special case of the formula that I'm going to derive. So maybe to start, I guess a vector function is similar to a normal function. Imagine if we have this maybe vector function like this, and we'll call it r of t with the little vector hat on top. And so the way that r of t works is you'll start in some, I'm assuming this r of t to be n-dimensional, but I guess for a demonstration, let's assume it's two-dimensional, and then maybe its origin is right here. So r of t, when you plug in some parameter t, you get out a vector that would point out like this along the line. And so it tells you where to go. You create all of these position vectors and so on. And it creates this nice line here, our curve. So we want to find the length of arc of r of t from, say, a to b. So might be best if I'm going to get rid of this r of t, and I'm going to blow this up. Resize, okay. So this is our r of t. Okay, now some things I want to do is, so how can we approximate arc length? Well, I know I'm going to end up using an integral. So what I'm going to do is I'm going to divide the length of this curve r of t into a bunch of different line segments. Okay, so let's say we start at some t naught, and we'll call that a. And then we go to a t sub 1. Now, I can connect those 2 points using, now for right here, it looks like they're right on top of each other, and we could call this t1, and then they could be equally spaced like this. And maybe at this loop it shows it better, but so like here where it's really curvy, the segments aren't drawn exactly. There's a little bit of error in our approximation, the curvier that this function gets. But the idea is that we can approximate it with line segments, sum up all of those line segment lengths, and we'll get our arc length as the distance between our intervals of time, or our parameter t, go to 0. So, and then we'll end with our t sub n length, and maybe this is t sub n minus 1, so a bunch of stuff happens here, and we'll call that b. So we have a being equal to t naught, which is less than t sub 1, which is less than t sub 2, which is less than t sub n minus 1, which is less than t sub n, which is equal to b, so, or which is just equal to b. So our delta t is, of course, b minus a over n. In other words, the change in distance of the change in our parameter t. So from, say, here to here, or from here to here, or any change in t. So it's also t sub I plus 1 minus t sub I. So to approximate, I'll write it out in words first, but so to approximate our arc length L would just be the sum of these segments. That's the idea. And so approximately equal, which is also approximately equal to, so I can write sigma I equals 0 to n minus 1. I indexed from 0 to n minus 1. You could also do it from 1 to n. You'll see it won't really matter all that much of just the distance of those length. Oh, he exploded on media. Anyway, so in other words, of t sub I plus 1 minus t sub I. Okay, so now what can I do with that? Well, there's a little trick, I guess you might say, and it's the mean value theorem for vector functions. And it's very much the same as the single variable calculus case that you're probably more familiar with. So it states that basically if I have f of t sub I plus 1 minus f of t sub I over t sub I plus 1 minus t sub I, that's going to be equal to, and these are all vector functions, that's going to be f of t sub I, f prime of t sub I star for some t sub I star being an element of the set, or the interval t sub I to t sub I plus 1. So basically it's saying the same sort of stuff as the normal mean value theorem. There's a point where the slope of the secant line going through two parameter t's of this vector function equals the slope of the tangent line at some other time in the interval of the vector function. So what we can do is we could write, I'm sorry, this should have been not t sub I, it should have been r of t sub I plus 1 minus r of t sub I, because r of t sub I would be here, say, or let me put in the laser, it'll stand out more. R of t sub I would be, say, here. R of t sub I minus 1 would be, say, here. And so the distance between the two would be this length here, and that's what we're summing up as those segments. So now, using the mean value theorem, we can replace that with sigma I equals 0 to n minus 1 of, now I'm going to multiply the mean value theorem by t sub I plus 1 over t sub I, I'm going to multiply by the denominator is what I'm going to do basically. So I replace the r of t sub I plus 1. I'm going to replace that with r of t sub I star times t sub I plus 1 minus t sub I, but that is just delta t. And so like I said before, if we let the number of those segments get bigger and bigger and the distance between those approximating segments get smaller and smaller, then we'll get the exact arc length. And so the exact arc length, L, is exactly equal to the limit as n approaches infinity of the summation from I equals 0 to n minus 1 of r of t sub I star times delta t, which is just the integral from a to b of of r of t sub I. And I don't need to put the star, although I could. The star is just really a dummy variable now because this is a definite integral, so it's just a number. I guess I'll keep the star, why not? Times delta t, or no times delta t, just r of t sub I star dt. And technically we're taking the magnitude of it because from this first step here we were taking the magnitude because it's a length. Its lengths are always positive, so we're taking the magnitude of the length. If the actual subtraction yields a negative number, we want that number to then be positive. So that right there would be magnitude, magnitude, magnitude. And so, this should have been a prime, 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 because this is the derivative, because it's the mean value theorem. So this is the most general formula for arc length, and I guess I should probably write it out one more time. Integral a to b, and you'll normally see it as just r prime of t of just t. You'll just see it as t. Doesn't really matter whether I put the sub I or the star dt, and it'll be the magnitude of that. So this is actually the most general formula, and in our on the FRQ that you did before, where you had to take the arc length of two parametric functions, it was x of t and y of t, and it claimed that the arc length was the integral from a to b of the square root of x prime of t squared plus y prime of t squared dt. And now that is true if r of t, the vector function r of t, is two-dimensional. The Pythagorean theorem is kind of a good way to think about it, but it really does come from this more general formula, which is a lot cleaner to write, in my opinion. And also, once you have this general formula proven, you can then prove the specific case that you learn in Calc 1 or Calc 2 class for arc length. So if we take any if we take any function f of x, which is a two-dimensional function, in other words, it lives in R2, the xy plane, and this r of t is not given that limitation. Again, it's n-dimensional, we assumed in the derivation. So if we assume to be in two-dimensional, and we take some f of x in the xy plane in two dimensions, and we reparameterize it in terms of t, then what we could say is that this f of x could instead be written as a vector function. And that vector function, call it r of t, would have components t, f of t, and 0. So you plug in some t value, you get out some f of t value, and z is just held constant at 0. So it's still in the xy plane. In other words, this is just a reparameterization of f of x in terms of t. Now, if we were to, all we have to do by this arc length formula is just differentiate r of t and then find its magnitude. So r prime of t, and we can just differentiate component-wise. We get 1 comma f prime of t comma 0. And so then the arc length of any two-dimensional function is the integral from a to b of, now we take the magnitude, so that's the square root of 1 squared, which is 1, plus f prime of t squared dt. And that is exactly the arc length formula from Calc 1 and Calc 2. Normally you'll see it written as f of x dx, but it doesn't matter what variable you use, it's a dummy variable, because again, this whole